Well, let's start, since I can't find it in my pockets. There we go. Let's start by a little bit of thanks, because I'm just the deliverer of some information from a big project known as EcoGig. It's had 2 runs as part of the GOMRI, the Gulf of Mexico Research Initiative. A lot of people have been involved in the projects funded by GOMRI, many of whom are in this room, and some of the big consortia. Our leadership is in this room, Steve Morawski and others. And so I simply want to point out that while I've got myself, Howard Mendelwitz, who's a chemical engineer in our group and has been working with us for 25 years, also physical oceanographer Harvey Syme, we've sort of been driving the data analysis and so forth, but other colleagues, including PhD students, now elsewhere, Dan's at Harvard, Laura's at University of Maryland, but Vernon Asper at USF. I'm sorry, USM, sorry. It's a little slip. Wonderful seagoing colleague. Cedric Megan at University of Maryland now runs their stable isotope stuff. Wonderful analyses. You'll see some of his data. Some of Ian McDonald's slides. Ian heard about me giving this talk, and he drove down from Tallahassee just to see his name on this slide.
I thought you had to put it in there.
Yeah, it was there. Some wonderful PhD students in our group right now. Adam Rock, really good with the ADCP data that I'll show you. Tim Wall, who's a wonderful analytical chemist who's using MC's technology that was developed here at USF through the Byrne Lab, and with Sherwood Liu as our star of making that instrumentation go. And Mandy Joy, who was the consortium director for EcoGig, who contributed some of the data that we'll look at. You've all seen these slides, but so when I give a talk about EcoGig, I look at a few of them because the focus was so much on the surface to begin with, and still is for some logical reasons that we'll look at. But our focus is on putting landers on the seafloor and looking at what's happening very close to natural seeps in the hopes of learning things about how to deal with accidental wellhead releases as well as natural seeps themselves. So some of these slides were taken by others in this room, so I'll just run through them real quickly. The wellhead, the flow out, Ian played a major role in deducing just how much oil and gas was coming out of this pipe. Ian, 7,000 psi pressure around that at the wellhead. Incredible that it was sealed. Those of us with an interest in gas hydrates in the Gulf, I don't know if we laughed or cried when they put that containment device over the wellhead claiming that they were going to seal it that way. That was kind of a sad joke. And so some of you in this room are more oriented towards this kind of look at things where we have gas and oil coming up to the surface forming oil slicks, the famous marine snow happening. Dave Hollander in the room here somewhere involved in the bathtub room work and ring work out there at the depth. Lots of people here know about this stuff, so I'm going to go fast so I can get to the data that I want to focus on. But I want to start out by making the point, this figure given to me by Mandy shows what people were looking for when they were first thinking that there were plumes potentially down there of oil droplets and of gas, thereby creating oxygen deficits and so forth. Things became more sophisticated when people began to realize that there were subsurface plumes that were forming at various heights. So this is just a representation of that possibility. What I put this slide up for, though, to show you is natural gas is the red in this little cylinder. Black is the liquid oil coming up. Ian, I'm not actually sure who generated this. This was from Mandy's 2011 paper that all of you, I think that's a very good paper to get introduced to this kind of information. Okay, let's move along. Ian generated this slide that basically is sonar hits on where there are seeps along at a station called GC600. And we're going to focus our attention in this talk at lander sites in various parts in this area, down here to the southeast of Megaplume. Megaplume up here, a seep with a name that Ian created for it. Here, in fact, is Megaplume, and I'm hoping it'll run. This is Ian's figure showing what's going on at one of these seeps. And if we have time at the end, we're going to look at some asphalt seeps where it's less vigorous, but just as interesting, I think. So to get to the point right away, so at that time, Over the side, we're going rosettes, water samples being collected, analysis being done, and it generated data of this kind. Interesting looking data. And by the way, there have been surveys of methane to ethane ratios for a long time in the Northern Gulf. Used to be through the NRL labs, Swinnerton, Lindenbaum, LaMontagne, names that we've long since sort of stopped quoting. But there's some really good background data up there, and I have with me a file of all of those. If anybody's interested in those from a literature study, I have them easily available. Methane at atmospheric equilibrium will be in the order of 2 to 3 nanomolar, so down here. Cedric Magan generated most of this data, beautiful stuff, and Mandy Joy's group generated some of it. But what I want you to notice, and some is within, near Plumes, outside of Plumes, some of it's at GC 600, just near the site. So the blue data, the green data are Cedric's data, and the red Mandy's. But you see what they both found was a subsurface near bottom max, actually more or less so within 100 meters of the seafloor. So going from atmospheric, sometimes background, sometimes a little elevated, and some dispute about what the uncertainties are in some of these numbers, but typical when you're working at these low levels of methane. And I'll simply point out that this involves bringing a bottle up, extracting the water, trying to prevent any degassing, and doing a gas chromatographic measurement. So pretty good data, but there's clearly a subsurface maxima here down hugging the seafloor. So that really attracted my attention. Here's a couple of slides from Ian showing where this was going on in the surface slick. I've loved this slide always, Ian. And what I want you to notice are these little squiggles that Ian showed us. Let's go to a little closer up. Natural seeps. And so he's our leader in terms of chasing these seeps. And how many, what's the count now, Ian?
5,000.
It's incredible. And so if you look a little more closely, you can clearly see as the water is moving around, not surprisingly out there, you yeah. Okay, so you can see that we can while we have the big slick up here, and I didn't say that, but the height of the slick action, we're still seeing these little persistent plumes at the surface. And I'll leave it to Ian to show you pretty pictures when the bubbles rise. Sometimes they're coated with oil. Sometimes you'll see a little sheen, even when you're on chipboard. I think GC 767 now remains the place where you see the biggest amount of that. So I want to ask some science questions, and I want to move right along. How do both biogeochemical and physical processes control seep-derived methane? And when I say physical, I really mean advective transport processes and so forth. Can we quantify methane fluxes out there? How do we, and associated microbial processes, how fast do the bugs get after the light hydrocarbons that we're talking about? Can we get ready for the next big one? There are leaky wellheads all over the planet. So we talk with people in Norway who are concerned with North Sea stuff, and they have the same interests that we do in monitoring things. I'd rather work in the Gulf than the North Sea, but all that aside. So our experimental approaches were to try to develop and deploy sensor arrays on benthic landers that could get us close to seeps so that we could get time series. If I were to pick one thing for the students in this audience to say, it would be, it's one thing to go out and collect campaign-style wonderful samples and get this wonderful analytical data and do it very precisely. I myself believe that we're missing time series data in a big time way, and that's where the future lies in part, is getting after time series data. So that was our focus, and with the possible funding from GOMRI, and we lucked out and got some. We also wanted to develop capabilities to target hydrocarbon releases closely, where they were coming from. Can we follow things? Can we follow a plume? Okay, so this is the sort of little dramatic slide to say it, not in words, but after Hercules went in shallow water, admittedly, and self-sealed and stuff, we were still left with this question: can we monitor methane sources, transport, and fate in situ? Can we get after this down deep where we haven't been able to work effectively in the past? And I think you all know about how sort of desperate the situation was, where we knew this thing was, the Macondo wellhead was basically losing, 15% of the total hydrocarbon reservoir maybe? And we weren't able to really even understand anything other than there's a huge amount coming out. Where it was going was still a mystery. So let's take a sort of a broad look at the EcoGig thing and where it's worked, and again some names up here of people that worked with our team at some of these sites. And I'm going to focus in on just a couple of them. I'm going to focus in on GC 234 and GC 185 isn't on the slide, it'll show up in the next one, GC 600, and one that I added to the mix, and you can see here anthropogenic release sites, natural seep sites, sites where there's cold water corals or deep water corals that we're not going to have time to talk about. That's Chuck Fisher, Eric Cordes, and that group that are leading that control sites where there are less influence of hydrocarbon releases, whether natural or from leaky sites. These are the ones where I'm going to show you some data from today, although not at 767. Horn Dome, I'll show you why we worked there first. The Deepwater Horizon site there in flames. A bad joke probably. GC 185 and GC 600 I just mentioned. Before I go any further, I also want to say that one of our strategies, because of the limitations of money, was to partner with private industry. I think we'll be seeing more and more and more of this in the future. But my particular partners are Monitor Instruments, Cheswick, Pennsylvania, sadly now out of business with the death of Tony Duryea, who helped invent the quadrupole mass spec. And we're using his new technology called linear cycloid mass spectrometry. Divalogic, whom we're working with a lot, expertise in communications with gear, construction of mini landers. We're working with them very actively. Franatech will come into the picture. It's a German company that was first putting out little small methane sensors with a little simple chip technology that tend to age over a 6 weeks period, but you can get some initial data before they go bonk. But they have come up with a laser sensor that has very low power compared to other laser sensors that are out there now. So they're on the edge of that. And of course, our old buddies, Andra Data Instruments. Last time I was here, I talked about sponge nitrogen cycling at Aquarius. And so I'm sticking with my buddies because we use their optodes to great advantage, plus their new ADCP, their little 600 kilohertz ADCP units that you'll see some data from. So we've enjoyed working with them. Without them, we wouldn't have the gear that we have to work with out at site. So here's GC 600. We saw earlier the larger scale photograph of it, and we were tending to work between 1170 and 1222 meters at this site, and I'll show you some data from that site. Landers put down, this is just a glorified close-up of that site, also indicating Ian's data, and the color scale goes from when there were multiple hits. I believe red is when there's 4 hits within a block, this data gotten over a period of years. Ian, where is this data published? I actually got given this slide by you.
We haven't published that data yet. That's from the Falcor cruise.
Okay.
It's just grading the number of hits.
Yeah. Okay, wonderful data because it allowed us to make choices as to where to put landers when we initially only had single landers to use. And so we went for sites along this ridge. You can see our choice was because of the enormous number of sonar hits of gas bubble plumes leaving the seafloor. And another way of saying it, but I put this one in just because I had put better looking stars in there where our landers went down. Okay, so these are our initial landers, big landers that had on them power sources. We had out to the side, out of the picture is some of the gear that went in, but we had METS sensors for doing some of the first work, but also ADCP information. And we were able to locate these things close to, for example, in this case, mega seep, a big known hydrocarbon seep located. So we had one lander. I'll show you data from this one, put 34 meters away from that seep. Here's the first ever time series data from a free vehicle lander in the deep sea, gotten in 2012 using METS sensors. Part of this is variability, but the sensor is going to fade out. This is a background site with the same kind of sensor system. So 2 different sites, OC26, a background site, actually near the Deepwater Horizon, near the Macondo wellhead, and then over at GC 600. And so we were beginning to be able to do time series measurements, and the measurements are continuous. So these aren't 1-point spikes or anything, it's a continuous measurement. And the only question is, what's the response time of the sensor? It's a membrane equilibration sensor, and I'll show you the membrane surfaces that you equilibrate through here in a minute. We also collected ancillary data along with that. We were watching tide range. I'm a long time ago interested in what happens when you change pressures to gas release from environments, and so we could and we did monitor this for depth, but we also picked up the tides very nicely out there. Average current velocities and speeds, centimeters per second, you're seeing we're between 5 and 10 when you time average for, this is sort of a running 3-hour average. We were also measuring oxygen, and if we have time, we'll talk about what the difference is between red line and blue line. Basically, we're putting open cylinders down on the seafloor and measuring current speeds going across the top of those open cylinders, big ones, 30 centimeter diameter, 1 meter tall. And we're trying to make use of the oxygen gradient that's created by sediment oxygen demand. That concentration gradient, when measured by a diffusivity, if you can calculate one for inside the chamber, can give you a sediment oxygen demand. So we're very greedy in what we're after. Here, temperature, and I wanted to point this one out since you guys are all survivors of Irma. Look at what happened when Isaac went over in 2012. We were in 1,222 meters of water. We saw an oxygen drop, and you can see that that's on the order of 10 or so micromolar, maybe a little more. And look at the temperature go up. So the guys at Woods Hole that are working on this particular issue know that there's large-scale sloshing going on, but isn't it interesting that you can see a hurricane going over because of that large-scale action and multiple sensors there varying. So this is the first kind of plot I'll simply show you. These are concentration rings in nanomolar of methane and direction. So it's simply an attempt to see if there's, and these are from 2 different sensors on the seafloor at different heights above the bottom. And so these are METS sensors again I want to mention. We'll come to the laser stuff in a minute. You can see that we're typically seeing stuff that's like that subsurface maxima that Cedric Megan and Mandy Joy's group found. Sometimes a little higher, up into hundreds of nanomolar. Okay, so what you do with that data then, if you have current, speed, and direction data, is you follow the water around, right, a vector diagram, and we can actually, what we were looking for was changes in methane concentration as a function of where the lander was relative to the mega plume site. So we didn't, this is kind of hard to see, but when we're close to that site and the water's coming from it and over it, we see relatively high methane. And so we're actually seeing this plume of methane-rich water going over our lander. So we were cutting our teeth on how to deal with what's happening down below with a single lander. This is the new evolution. Am I going too fast, or is this okay? We want to have time to see Ian's asphalt volcano stuff. I do anyway. Anyway, so here's a laser sensor with the membrane surface, specialized membrane. You get some sense of it. I'm sorry I didn't put a ruler in on the shelf, but you can see a drawer from a bench if you're on a laptop computer, gives you some sense of the size. And we're watching what's happening in the room with methane, super sensitive. This kind of laser sensor, of course, has been used in atmospheric chemistry for decades. Aerodyne Corporation put out methane lasers long ago. But but down deep, it's only recently that these sensors have become available at all. They're still very expensive. The list price for this baby is $87,000 each. It depends on fluctuation in the euro, of course, but they're super expensive. So working with the company was a tremendous advantage to get the breaks we got. Here's a test of this laser sensor in our lab. It's a pumped sensor. You don't get enough diffusion. You want to keep the water flowing over that membrane so that it can equilibrate with the interior of the laser sensor. I should have said that. So the water is moving over this membrane. It's equilibrating with the guts where the laser diode is, and the question is, what's the equilibration time? Hence a pretty big membrane, fast as possible. There's fighting going on about this. I think that the equilibration time is on the order of 20 minutes, something like that, and the company is claiming 30 seconds, something like that, but they're computer analyzing their data and looking for maxes and mins and all that stuff, and so I'm still sticking with my 20-minute time frame, which is good enough for working underwater on a lander, not necessarily AUV stuff, right? So, okay, here's a calibration in our lab of their sensors, and you can see these are GC measurements and so forth, and we're following their moving average And so we're just attempting to make sure that this thing is working. It initializes, we bubble some methane into a tank to get us up to a couple hundred nanomolar and watch it with time. So we were pleased with the performance of this laser. And I want to say right now, this laser represents a calibration tool as well for MIMS. MIMS, underwater membrane inlet mass spectrometry, it's notorious because of its temperature sensitivity and so forth. So having a tool that is that compensates for temperature and so forth that you can use in a laboratory and then calibrate the MIMS underwater is a big deal. So I'm after combined sensor methodologies in the future. We got a chance to test this laser when Mandy had a 2014 cruise and went out to GC 600 area, sub going over the side. Here's our laser sensor on the bottom on a little stolen plate from the ship. We shouldn't mention this. Don't ever mention that you saw it. We stole a deck plate, mounted things on it, put our little power pack on there and put it over the side with a little conductivity sensor and some other sensors. But the main purpose was to get down there next to a seep site as shown by the little T-bar here and make some measurements with the intake for the pumped laser. We also had Z-pulse for single point acoustic Doppler current, speed, and direction measurements. There's a little close-up of the seep there, and here's our little tube poking out towards the sensor. So we're within tens of centimeters of a bubble stream that's coming up continuously. And you saw some of the bubble streams earlier from video that Ian had shot. Okay, here's the data that came from that. This is in 2014 that we were able to do this test again. So two different scales for methane. Methane's the middle panel. Let's focus on that. Water is moving around, don't forget, but 100 meters away from that platform, when we take it 100 meters away, away from the seep, we see something like, is this initializing, something that's from 20 to 80 nanomolar methane. Very much like what was being seen by water grab samples near the seafloor. If we stick the snout in within tens of centimeters of the seep, we see that the gas bubbles, as they rise, they dissolve. In shallow water, they lose about 10% of their mass every 10 meters rising through the water column. So out here in Tampa Bay, where stuff is bubbling during low tide action, if you've ever seen that going on, it'll be losing about 10% of its mass. You use the same model that you use for air-sea gas exchange to determine it. What's the thickness of a laminar boundary layer around bubbles? About 5 to 10 microns is the number you would use in a model for methane injection by rising bubbles. Here we're much deeper. The bubbles, higher pressure, they're equilibrating with the surrounding, and we're seeing up to a little over 4,000, head towards 5,000 nanomolar methane. So that's what you can expect as the bubbles are passing through a layer like this, maybe higher, maybe it'll be 10, 20,000 nanomolar somewhere. It's not going to be in the high millimolar range, and when you're down at 1,200 meters depth, right, you're at 121 atmospheres or so. Multiply that times 1.4 millimoles per liter atmosphere for methane saturation. You have enormously high concentrations of methane to make a bubble. So this is still a small fraction of what might be when bubbles come up. Okay, we've already looked at that. Here's the response time issue that I want to show to you. We have two MET sensors and one laser sensor showing here some oxygen data as well. And what we're just keeping track of. And look at these response times and the delays in returning. So there is a response time issue that we'll talk about. Well, let's get into the meat of things real quickly. This is what we call a mini lander. We can talk to it acoustically. So this is our device we hang over the side to talk to our acoustic. We can actually retrieve data from it when it's down on the bottom. We typically here we were just releasing it using the pingers and so forth, but we typically put this thing over the side with a launcher and we'll put it within 10 meters of the seafloor and drop it. Has a steel plate on the bottom that's out of sight that you can't see, and it'll land on the bottom squarely. When you want to retrieve it, you drop the steel plate and call it back up. We now also have pop-up buoys on this side. One of these blocks actually rises up, takes a little hose up with it. We've set it up for 10 meters above the bottom, so we can actually measure methane. Here's the laser. We have an intake tube. All the electronics are in the battery pack here, the head of which has the communications package as well. for talking to the other sensors, including optodes that we may have time to talk about or not. So we're mostly stuck at so far with lithium batteries, and you can only use the ones that are safe under load. And so 220 amp hours, 230 amp hours is what we can get down. And I think you all know how expensive those batteries are, 15 bucks a piece. We're putting 131 in per load that goes down. So we're spending close to $2,000 every time we put a mini lander over the side on batteries. We really want fuel cell power and or whatever else is going to come that we're after. At any rate, that's a mini lander. We'll talk about the chimney here if we can later. We're still working, no, we're not still working on it. Just kidding. So let's first look at some data from Horn Dome, and I'll tell you why it's all the fault of the physical oceanographers in this room. We went out there going to our we wanted to go to GC 600 to start with, and look at this eddy off the loop current that we ran into. The thing was 3 knots at the surface, so that's on mark. And so it was really moving. We couldn't go there and start, but I love this picture. What a dynamic place the Gulf really is. So we chose to go to Horn Dome over here, about 100 miles out of Gulfport, and other sites, but we were coming out of Gulfport using the Point Sur. Here's what Horn Dome looks like, and here's acoustic data. Ian, I don't know whether this is yours or someone else's, the green dots at Horn Dome and so forth.
I think that's OE.
Okay. All right. This data was available to us on the ship, and so we steamed back in. Vern and Asper had access to it, and we chose to put our mini landers, 2 of them, down here and here on Horn Dome, and that's just to give you some depth contours. Let's go past that quickly. And here's the crew, and Thomas is an engineer from DevaLogic, so they've been a great company to partner with. They send their engineers, their best ones that work on this gear, with us. Arne Vesselin, Vernon Asper, and Howard Mendelowitz, the chief engineer in our crowd at UNC. Getting ready to put the baby over the side, and here's what we get. And I think I'm going to show you a couple of slides as we clean up the data. You can already see that at this first Horn Dome site we were seeing the same kind of things that we saw with the METs. The advantage is the laser will go for a long time and you can duty cycle it. MET sensor, you turn it on, it has to heat up. I think you know what that means in a cold ocean. We're down here at 5 degrees Celsius, something around that. It's a huge power sink, and so being able to duty cycle is a big deal. So we're on 3 hours, off 3 hours, and that's why there's gaps in the data. Does that make sense to everybody? We then further, so here's a short period of time from the 4th to the almost to the 6th of September from 2015, and you can see what we're really seeing. There's a combination of processes controlling this methane data, and I'll again point out to you that this kind of data wasn't being gotten before, so I don't apologize for the corrections we're going to have to make to it. But what's happening is, as the water flows by, you already know that methane concentrations are going to be changing, right? It's moving around the lander in a fixed place, but there's also a response time factor, and that's why that's such a big deal for us. So we further treat this data to eliminate the first 2 hours of data every 3 hours to let it smooth out. And so we're in the process of deciding exactly how we're going to represent this data. We're fighting about the response time of the sensor, basically, I will say. Okay, but you can see that we're in the ballpark of what we were expecting to see at Horn Dome, so we were encouraged by this very first deployment of these guys and proceeded to go on over to GC 600. So let's, I'm sorry. We proceeded over to GC 185 first and put down, we had to pull it back up after we went down and looked a little bit. Bush Hill, GC 185, this area well described by Ian McDonald in his publications and other people from the past tube worms and so forth, but look at the bubble streams, that's why we were interested, and a really nice gas hydrate deposit. And look at this data that we got. This is what we can see if we save enough power to leave it down for a month or so. But we first query our lander to see what the quality of the data is. And so this is what the instrument is warming up and turning on. And we're seeing over 100 nanomolar methane at Bush Hill, so we know we're doing okay. So we left the lander at that point and we proceeded over to GC600 to do some other work. So I want to show you some work from GC600 now where we used the pop-up buoy and everything else. Here's a picture of our little lander on the bottom. The tubing hasn't yet been pulled off, and in fact we actually had a problem with getting this thing off the little lander, but you can see this cylinder that for oxygen gradient measurements that we may or may not have time to talk to. This is a lander, the iSpider from University of Mississippi, Howard helping to do the deployment. Here's the kind of data that you see if you have a pop-up buoy and you're working down right next to the seafloor and you're collecting methane data 1 meter off the bottom, the red line, and 10 meters up. The pop-up buoy up in the water column with the hose running back to the pump that pumps it over the laser sensor and over all the other sensors that we have down there at the same time. Okay. I think I put that in there because this one was messy to look at, so we'll go past that one. This is one of my favorite things to do. I really love to watch things in motion, so why not? There's a methane down in the bottom. And you can see, this is the way I want to think about the time series data that we're getting in the deep sea. Sometimes there's high methane, a lot of times not very exciting. The concentration over here is less than 50 nanomolar sometimes, but you can see in the past we're sometimes up in the hundreds of nanomolar. And so on it goes. The only limitation is, of course, power. And that's why the 3-hour gaps. And it's also a threat to your instruments to turn them on and turn them off. All of you that work with deep sea instruments know this. So, I want to show you what our little ADCPs began to give us once we were able to do profiling. We're using, again, the new Andra data instruments, 600 kilohertz jobs. They only cost about 15K, so they're not as bad as the big boys, maybe 12K. So here's current recombined centimeter per second speed, and here's the direction. And I don't know if you can see the 0 to 360 and up to 25, up to 35 centimeters per second. And so we can look at what's happening in terms of both speed and direction as a function of water depth, and these things are good for maybe up to 20 or 30 meters above bottom. So they're ideal for our purposes. They're not particularly good for dealing with out of the friction layer, obviously, which is probably on the order of 50 to 60 meters in thickness against the seafloor. And it's a wipeout below 2 meters, as I should mention. Okay, so you can see that there's pretty normal flow a lot of the time, and the reason I'm showing you this now is as we're getting towards the concluding slides of this kind of data, I want to show you coherence when we were able to get together 3 mini landers and we triangulate around sites now. And we've had a recent experiment where 2 of them worked. Okay, so here's the data put together along with an actual vertical attempt to get at vertical velocities, which are on the order of less than 5 centimeters per second, compared with that methane data. Of course, what we're after, as I think you all know now, we want to deal with the transport of methane. We're after fluxes down deep. We're not just following concentrations. We want to know about plumes, hence the title, Methane Plumes in the Deep Northern Gulf. Okay. Horizontal, but just to average this out so you get some sense of it, the direction, on average, 200, okay, compass. And average speeds, well, those went through a sizable change during the period of time that we saw, but you can see that very commonly at those kind of depths we're over 15 centimeters a second, and we see speeds exceeding 30 centimeters per second, so we're well over a half knot, and sometimes we see half knot currents within the friction layer out there. Vertical depth average speed, so the much lower as you might expect. Negative means down and positive up, and so we think we can deal with turbulent action out here. So we're a little pleased with these little ADCPs on our landers, and we can handle the power. Let's say something about, it's not letting me go back. I wanted to say something about our future applications, but let's skip past that, just gas hydrate pictures. You've all seen these before. It's Mandy holding a pan full of stuff in the laboratory, which is completely illegal. You're supposed to keep them outside on the deck. And you're not ever supposed to light them on fire, right, Ian? Yeah. He taught me how to do it. Okay. So here we have a triangulation experiment that we've just completed. The ship And it gives you some sense on scale. In reality, let's just say these things, this distance is approximately 100 meters. But because of our launcher capabilities now, we can put down 3 of these little mini landers right around a seep. And of course, we could put them down around a leaky wellhead, right? So we're now operational in terms of being able to do that. What we need is more power so we can stay for longer when we're doing this kind of thing. Because I don't want a duty cycle on a much longer time period than we're doing. Okay, so here's the latest Bush Hill data set from fall of 2016. We're through collecting data. The EcoGig 2 project will end as of December, and we're in wrap-up. But this is the same kind of data that you're looking at. So here's 1 meter above the bottom methane at GC 185. And notice we're up at 300 nanomolar concentrations, pretty high. So you know you're getting pretty close to those bubble rising places where it's in the thousands of nanomolar, okay, with this particular lander that we're choosing. This is ML number 1. We filter that data by taking 5-minute averages. 5-minute averages are shown here, so as to get rid of some of the noise in the stuff, the water going by, up, down concentrations, and also the response time issues that we're still working with. But you can see what we've got going. And finally, we'll take it to an average of the last 30 minutes of each 3 hours, when we're pretty confident that we've got the response times in good order, and we've had a period of relatively constant concentrations. And so you can see that during initialization, there's some action there, but we're seeing something in the hundreds of nanomolar when we get close to any one of these seeps. I think I'm going to save some time. How are we doing for time? Okay, we're good. Okay, let's look at ADCB data from two landers that were around, just to give you some sense of it, how the landers were oriented in case anybody's interested. But let's look at what's going on with interpreted speed. These are 1 hour, 2 hour, 3 hour average data. Okay, 1, 2, 3. So let's just look at this one. You can see that speed, direction, we've got the typical speeds that we've been looking at in centimeters per second, and directions randomly running around. So how well can we compare? Let's just look at these loader patterns. How well can we compare 2 of these ADCP systems? In other words, landers 100 nanometers apart. So I'm going to compare this set with the previous data set. ML1 versus ML4 current 3 hour average. And you can sort of see that we're at low current speeds during this particular time at both sites. But you're seeing, even on a 100-meter scale, sometimes little bursts of transport. Those are within, the error analysis has been done rather carefully by Tim Wall and Adam Rock, working with Harvey Syme, who knows what he's doing with this kind of data. So these are for real differences between the two. So current speed at ML1, current speed at ML 400 meters away, pretty much the same. We didn't see any big events during this particular deployment. Direction, also similar, but there are subtle differences and so forth. And so if you're really, I guess what I'd like to say at this point, looking at this kind of data, if you're going to hang a bottle over the side of a boat and try to get after methane transport processes, let alone concentrations, you're lost. You need to be at a fixed point if you're working with landers or whatever else. You have to be able to swim very effectively around and cover a large area to get after what's going on with these plumes that are going to be in the news again. There's leaky wellheads all over the world, as we all know. I think I want to say something. I guess the ancillary data here, as we're going along, we're monitoring oxygen concentrations and temperature at all time, and you see the expected relationships. The deep water out here is Antarctic deep water, North Atlantic central water above it, and you see mixing between the two of them, and so you see the expected stuff. The expected thing for O2 temperature relationships, and I just said that. So we're able to well define what's going on from a water mass point of view. I think I'm going to avoid getting into the mean directional speeds and so forth. So let's sort of jump to a little conclusion thing, and let's see if we have time for both a little bit of the sediment oxygen man work and Ian's video that I'd like to see myself. we calculated sediment oxygen demand rates from continuous current and optode concentration gradient measurements for the first time at MC 118 during an early gas hydrate project and so forth, and it looked promising. We did it for up to 160-day period. So we're talking about being able to monitor sediment oxygen demand for half a year in this case. We're really going for it, a little less than half a year, 5 months. And we're doing it with an open chamber. And so if there's a sediment flux in oil, snow, or anything else, we'll pick up that signal. The problem, of course, is that you create an artificial oxygen gradient within the chimney. Okay, so you're messing with the gradient near the seafloor. And so even if you can measure the current speed that's creating turbulence within it, you're going to have to be careful in how you determine it. So we'll estimate, we'll call it maximum sediment TOU, and that word maximum really matters. Total oxygen utilization. Okay, I'm using the term that the people that do sediment oxygen demand use to cover all the stuff that's going on. We'll calculate the eddy diffusivity. We'll make estimates from Trowbridge et al. Using von Karman's constant and stuff. And I should have put this slide first. So this is one of our ugly chimneys here. Here it happens to have MET sensors hung on the side of it. But we'll put oxygen optodes in a vertical array, and they're around the other side here. I apologize for that. But this is one that's just measuring ambient concentrations at this height and this height. And we get data that looks like this. It looks beautiful. The question is, what's the level of accuracy? There's no question about precision of the optode measurements. We're able to calibrate our optodes to do plus or minus 2 micromolar. So we're really on that. But look at what happens, and you're going down with depth into the chimney. Here we had an ambient and optode sensors at 28 and 20 centimeters above the seafloor. The red is the closest to the sediment, the green just above that. So we time average that data, and we get something that's you can look at, time average, and you can see what's going on. The dashed line is the bottommost sensor at 20 centimeters above the green line, the one at 28. So we're seeing a gradient, and we can calculate a delta O2 from that. So we actually this is a maximum TOU, remember, so I don't want to fight with people about the oxygen gradient. There's problems. We're just trying to get as much as we can out of this work. In the end, it comes down to, after we apply our eddy diffusivity, we get a total oxygen utilization that completely agrees with the kind of numbers that are being seen out on upper slope around the world, as summarized by the people who are the kings of sediment oxygen demand work. And so we were able to get away with publishing this data in Deep Sea Research last year. So that paper is available with that kind of stuff in it. Okay, I think I don't want to talk about that stuff. I want to say for 1 minute, and then I'm going to let Ian get up. I simply want to say that I was on a commission in the state of North Carolina about offshore energy exploration, and read this. By strange coincidence, within a week after this report was approved, the drilling rig exploded. This was a put-together committee. I was sort of a lone voice turning around my laptop and showing everybody that there was a big oil release somewhere in the world every 2 days. and the industry guys were denying. They said the technology is totally safe. And the committee was about to write a report, which here is being disallowed. But our report is worthless, is basically what the letter ends up saying. And it's a very fascinating experience. So I'm interested in doing this kind of work off North Carolina, and for some reasons that I want to show you now, and then I'll continue. I'll finish up. There's an area all along the upper slope, an outer shelf edge of North Carolina, all along the margin, going all the way up to Georges Bank, where there are massive seeps of methane gas being delivered to the seafloor. Let's just cut right to the picture first. So this is an EK-80 shot taken last year. Carolyn Ruppel's group and Reed Corbett at East Carolina and at our Coastal Studies Institute in Manio got these shots. These are huge, gigantic methane seeps. This is just a repeat. This is 171 meters down. These plumes, the Gulf Stream is going this way, are just rising up into the Gulf Stream. Nobody knows what's going on with the chemistry of these plumes, how much is dissolving, how fast it's being oxidized by microbes. John Paul's world. There's a lot going on out here, and it's in a really rough to work on environment, but I think we're up to it now with our little mini landers. So I'm going to conclude by saying you find methane concentration maximum all around the Gulf near the seafloor within the friction layer. It really jumps up quickly. Concentrations typically 10 to 300 nanomolar, but don't be surprised if you see thousands of nanomolar. So it's rare to get into the millimolar range. Okay, I remind you this is way below bubble saturation for methane. Deep northern Gulf waters are enriched in methane from seep bubble dissolution. We're somewhat better prepared to get ready for the next event. I think actually we're reasonably well prepared compared to where we were before Macondo blew out. And real-time data sensor may allow directed water column sampling. If we can have enough power to query our landers, and we know where methane is going, this can direct where we put samplers for collecting samples for microbiological degradation rate studies and so forth. So I think the combination of those things is going to be powerful. And I'm going to stop there and thank my crew again. So let's give some time for Ian, and thank you for listening to my part. Okay. Maybe I have time for one question or something like that. Kendra, then Dave.
Can you give us an estimate of how up in the water column